All right, ready to dive into something that seems deceptively simple, but gets really wild really fast.
Let's do it.
Today we're looking at Feynman, specifically Chapter 46 of the Feynman Lectures, the ratchet and pawl.
Oh, this is a good one.
Yeah, I mean, it's like we're talking about a little machine you might even have in your toolbox.
Right.
Right. But Feynman uses it to bring up some really big questions. Like, what does it even mean for something to be irreversible in physics?
Exactly. And he does it in such an elegant way, starting with something so basic. You have this wheel with teeth, but the teeth are kind of special, right? They're like little ramps, all slanted the same way.
Yeah, and then you've got this little arm, the pawl, that rests against the teeth.
And that pawl, it only lets the wheel turn one way. So simple, but why?
That's what I love about Feynman. He makes you question the obvious. Like, we all know a ratchet only turns one way, but have you ever thought about why?
It's like he's saying, don't just accept it, figure it out. And the key is in those little details, those things we might overlook.
Right, like the spring.
Exactly. The spring in the pawl is crucial. Every time the ratchet turns, the spring is what pushes that pawl up over the tooth and then lets it fall back down.
So it makes that click sound, right?
Exactly. But without that spring, the pawl wouldn't reset properly. You wouldn't get that one-way motion.
So the spring keeps things moving in the right direction. Okay, but then there's this other part, right? Damping.
Ah, damping. This is where things start to get really interesting because it brings in this idea of energy being lost.
Okay, so walk me through it. What is damping, and why does it matter for our ratchet?
Okay, so imagine if the pawl, instead of being a rigid little arm, was like a bouncy rubber ball.
Okay, I'm picturing it.
Every time it hit a tooth, it would bounce back a little, right? And that bounce back, that's the kind of thing that could potentially let the wheel slip backward, even if it's just for a tiny bit.
Ah, I see. So damping is there to prevent that from happening.
Precisely. Damping could be anything from friction in the mechanism to air resistance.
Even that little clatter sound the pawl makes, that's a form of damping, isn't it?
Exactly. That sound is energy being lost as heat, and that loss of energy, it ensures that the motion really does stay unidirectional.
So even in this seemingly simple system, we're already seeing hints of thermodynamics, of energy transfer, and dissipation.
It's all connected, and it gets even wilder when we start thinking about how temperature affects the whole system.
Right, but we're going to have to save that for after this quick break. So we've got a ratchet and pawl held back by this little bit of damping, and you'd think that's kind of the end of the story.
You'd think so, but Feynman, he always has a way of taking things a step further.
And in this case, it's all about temperature. Like, what happens to this ratchet when things heat up, literally?
This is where things get really mind-bending because Feynman asks us to imagine this ratchet connected to something a little different. Instead of someone just turning it with their hand, we're going to hook it up to these tiny vanes like a miniature windmill almost.
Okay, so instead of a hand, we've got this little windmill thing.
Got it. And we're going to put this whole contraption inside a box. And that box is filled with gas molecules just bouncing around, doing their thing.
Okay, I can picture it, but I'm not seeing how temperature comes into play yet.
Ah, well, that's where the fun begins. See, the temperature of those gas molecules and the temperature of the ratchet itself, that's what determines which way the ratchet turns.
Wait, what? So you're saying, like, if the gas is hot, the ratchet turns one way, but the ratchet is hot, it might turn the other way.
You got it. Let's break it down. If those gas molecules are hotter, they've got more energy, right? They're zipping around faster, smashing into the vanes, and causing the ratchet to turn just like we'd expect.
Okay, that makes sense. More energy equals more motion.
But now imagine the opposite. What if the ratchet itself is hotter than the gas? This is where it gets wild.
All right, I'm ready for the wild part.
Because of something called Brownian motion, you see, the hotter something gets, the more all those tiny molecules that make it up are jiggling around randomly. So if that ratchet is hot, the pawl is vibrating like crazy.
So the hotter the ratchet, the more erratic the pawl becomes.
Exactly. And that random jiggling, well, there's a chance it could lift the pawl up just as a gas molecule hits the vane, just enough for the wheel to slip backward, even if the gas is pushing the other way.
So you're saying the randomness of heat, the chaos at the molecular level, can actually make the ratchet run in reverse.
That's exactly what Feynman is getting at. It's not just about the overall force, it's about the interplay of energy and probability.
This is blowing my mind a little bit. So are you saying that if everything, the gas and the ratchet, were the same temperature, the ratchet wouldn't know which way to turn?
Now you're getting it. At the same temperature, in perfect equilibrium, the ratchet would be equally likely to turn forward or backward. There'd be no preferred direction.
Wow. So this seemingly simple machine is hinting at something much deeper about how energy and probability govern the universe.
And this is just the beginning. Feynman takes this idea even further to explore the idea of reversibility and the arrow of time.
So we've seen how this simple little ratchet can act in some pretty weird ways depending on the temperature. But I still keep coming back to this question of, like, what does it all mean? What's the bigger picture here?
That's what's so great about Feynman. He uses these everyday examples, these little machines, to get at some really profound ideas about the universe itself.
And in this case, it's this idea of reversibility, right?
Exactly. Like when we write down the equations that describe how things move, how particles interact, those equations, they don't really care about the direction of time.
Wait, so you're telling me that, like, in the world of physics, time doesn't really have a direction?
In a way, yeah. The laws of physics, for the most part, are time reversible. But then there's our everyday experience.
Right, because if I drop an egg on the floor, it splatters. It doesn't, like, unsplatter itself and jump back up into my hand. Time seems to have a pretty clear direction in our world.
And that's the puzzle, isn't it? How do we reconcile these time-reversible laws of physics with the very clear arrow of time we experience in our daily lives?
Okay, so how do we explain that?
Well, Feynman points to this idea of entropy.
Entropy, right, okay.
Yeah.
It's a word everyone's heard, but I feel like it's often misunderstood.
Yeah.
So entropy, in the simplest terms.
Think of it this way. Imagine you have a perfectly organized deck of cards, all in order. That's a state of low entropy. Now, shuffle that deck.
Things get more random, right?
Exactly. You've increased the entropy. Now, could you shuffle that deck and get it back to that perfectly ordered state?
I mean, it's possible, but the odds are incredibly low.
Exactly. And that's what entropy is all about. The universe tends towards states of higher probability, and usually those states are more disordered. It's not that time can't go in reverse, it's just far less likely.
So, like with the egg, it's not impossible for a splattered egg to reassemble. It's just statistically so improbable that we'll never actually see it happen.
Precisely. And just like that egg, the entire universe is tending towards higher entropy, towards more disorder over time.
So this arrow of time we experience, it's not really built into the fundamental laws of physics. It's more like an emergent property of the universe's tendency to get more random over time.
That's a great way to put it. And this brings us to, perhaps, the biggest question of all.
Hit me with it.
What about the universe itself? I mean, if the natural tendency is towards disorder, how did the universe start in such an incredibly ordered state in the first place?
Right, because we look around and we see planets, stars, galaxies, all this incredible structure. How did we get here from a random soup of particles?
It's the ultimate question, isn't it? And Feynman, being Feynman, he uses this idea of the ratchet and pawl to illustrate it. He says, imagine if our observable universe, with all its order, was just a random fluctuation, a temporary blip of low entropy in an otherwise chaotic cosmos.
Okay, so you're saying there'd be these pockets of order, like our universe, surrounded by vast seas of randomness.
Exactly. But that's not what we observe when we look out into space. Astronomers see order on the grandest scales, which suggests that the entire universe must have started in a highly ordered state, a state of low entropy.
Which is why we have the Big Bang Theory, right?
Precisely. While we don't fully understand why the universe began in that initial state, the Big Bang provides the best framework we have for explaining how the universe evolved from that initial order to the more complex but ultimately higher entropy state we observe today.
So from a simple ratchet and pawl, we've journeyed to the edge of the cosmos, confronted the mysteries of time and entropy, and maybe even glimpsed the very origins of the universe itself.
And that's the beauty of physics, isn't it? It's all connected. The same laws that govern the smallest particles also shape the grandest structures in the universe.
And on that note, we're going to have to wrap up this deep dive, but hopefully we've left you with more questions than answers, more things to ponder and explore. Because ultimately that's what Feynman would have wanted for us, to never stop questioning and never stop being amazed by the universe and all its mysteries.